At first, let's go to take a look to the outline. It will be something like map to me. I will try to explain some important things. After that, you can take clear idea about the electric resistance, about the manganite oxide properties. What is the temperature resistance curve? I will explain two important things. The first one, the isolated metallic temperature transition, and the pure temperature, and which one will deal with the isolating metallic, which one will related with the magnetic properties. The double exchange mechanism and Jones-Taylor effect is very important to us, and I will explain why these two methods is very important to us. Some experimental research, actually I take some components from some articles, and I put it all the names of these articles at the last slides in my seminar. Okay, summary and reference, like I said before. Now let's start from the first form to the generic to the perovskite oxide AbO3, and in another source AbOX, like here in another source. Both of them have the same meaning. Ab, both of them are cations, and X or O is oxygen. And the important form will be to us about lanthanum manganite O3, 5 of oxygen. Here, another important idea about the manganese oxide has some property with many corners, with many fields. Let's start from electric properties, electrical resistance properties, magnetic properties, magnetic resistance properties. I wanted to say we have many fields related with manganese oxide, not just electric resistance, but my seminar title, my field, my topic will be on the electric resistance. Okay? Now, here, this important curve to us, it's the resistance temperature curve. Explain to us what that means, the isolated metallic transition, and what is the pure temperature. Here, at y-axis and x-axis, here I have the resistance about ohm centime units, and here the temperature on the Kelvin. Actually, we will start from room temperature 300 Kelvin and warming, cooling, something like that. Generally, the curve will start from here and suddenly increasing to the top and decreasing again, approximately equal the original point. Here at the top, by using another color to make this clear, at x-axis at the temperature, here will be isolating metallic transition temperature. Here will be isolating, here will be metallic. And the same situation, same idea about pure temperature will be from the top. We will drawing line at x-axis at the temperature to say this pure temperature, but here the elements will be from paramagnetic to ferromagnetic. That means here the magnetic properties will be stronger than the first part. Now, the double exchange and Jones-Taylor, all of these are very important methods to us. By using it, we can explain two important things. That is electronic interaction in manganese. The second one is explain the electrical magnetism in the perovskite oxide. Here, a simple photo, to explain to us what that means, the double exchange, actually at 1951, proposed by Zener. Here we have two fields about can take electrons. Actually, it's filled with 7 electrons. Here we have two different chains about manganite. 3 plus and 4 plus. 3 plus, that means I have 4 electrons. 4 plus, that means I have 3 electrons. Here, the last one at the top, at EG, has an opportunity to can jump from level to another. And this, the oxygen, will be something like a bridge to can take the electron from the first side and take him or support him to can do another jump to another side. To be continuously change from 3 plus to 4 plus to 3 plus and keep going. Here, some change about the angle after the perovskite is done. The theta will decrease, will be smaller than 180. Here, some comparison between double exchange and super exchange, and we can say the double exchange is more extractive than the super exchange interaction. And here, like I said before, the electron should follow the Ham's rule. All the vectors will be to up and will jump to here, and after that do another process and keep going to be from 3 plus, 4 plus and keep going. But at super exchange, this phenomena is a little bit different. Here, the direction is different comparison with the first one. And here, all the vectors side will be to down. Here, it's antiferromagnetic coupling. Here, ferromagnetic interaction. Now, let's talk about John-Taylor effect. John-Taylor effect, any complex occupying any energy level with electronic degeneracy is unstable. It's a fact, it's condition, it's unstable. Against a distortion that removes the degeneracy in the first order. Here we have another important thing in John-Taylor effect. Here it's divided by using this image from T2G, like I said before. Inside it, 3 levels. Here, 2 from this side will be dxz, dyz, and this last one is dxy. And the next level, the higher level, is divided to be dxy square minus dxy square minus y square and dz square. And here we can take a look. It's clear the length about the direction. Here it's little bit longer than, and here some change about the length. I am talking about the instructions generally, okay? Some difference from this side to this side after the distortion. Here we can say it's an important mechanism of symmetry breaking in molecular and solid state systems. Here, another phenomena related with John-Taylor effect about high spin, low spin. And we can say low field, high field. Here the idea in this image, let's say we have 5 electrons. In high spin, the spin has an opportunity to can jump from this level to high level. How? Let me explain that by use 5 electrons. Will be 1, 2, 3, 4, 5. That's right. But here the situation is different. With the same 5 electrons, will be 1, 2, 3, 4, 5. Not don't has any opportunity to can jump directly to the high level. If I use 7 electrons, that will be clear. 1, 2, 3, 4, 5 will be 6. Okay.
It's not about.
Okay, I forget it myself.
So I think that we can't do that. Wait.
I will solve it after by Parfan or something like that. Will be 6, 7. But here, 1, 2, 3, 4, 5, yes, 6, 7. But here, I must solve this blank and after that can jump to another level, to the higher level. Here, the electric resistance was observed in three slides, in three fields. The first one, polycrystalline, or we can say bulk manganese, thin film manganese, and the last one is single crystal manganese. Here we started with the first slide about the experimental research, some experimental research. Actually, the first component was that the same elements but with different construction. Here 6, here 55, 40, 45. What's happened? Here, this curve is resistance temperature curve. Illustrate to us the difference about the resistance. It will decrease or increase by applying different amount of current started from 0.1 milliampere until 50 milliampere. What will happen with these different colors? The first one is the black one, is the upper one, that's right, with 0.1 milliampere. The resistance is more than 80 centimeter. But when increasing the current continuously from 0.1, 10 until 50 milliampere, the last one, the resistance will be less than 60 centimeter ohm. That's mean when increase the current, the resistivity is decreasing. And like I explained at the previous slide, the isolating metallic temperature will be here. Here is approximately more than 130 Kelvin. But here the situation is a little bit different. Why? I have decreasing in the resistivity, but it's less than the previous picture. How? Here started from less than 40 or approximately 40, and with 50 milliampere at the blue one, it's less than 40 centimeter, a little bit decreasing, but we have decreasing. Then the next slide explains to us the difference between these two previous pictures. Here start the resistivity from 1 and finished to more than 0.9, but the concentration 0.4 started from 1 until more than 0.7. A huge difference about the decreasing between these two situations. And we can say all of this because the contrasting homogeneity of these two components. Here another component with when increasing the temperature, the resistivity will decreasing. Here at this part, here we're dealing with low temperature, all of the temperature with Kelvin. Here less than 50. What will happen? Approximately more than 0 until 50. Some decreasing like here, and after that will start to increase more than 50 Kelvin. Then we will apply different amount of current, start from 0.1 milliampere until 7 milliampere. And we will use IV care, we will see another behavior to all of these colors. Here, all of these colors, all of this amount of current will follow the ohmic behavior because all of these are lines. Here, we're talking about after the decreasing, after the topper one, and with different amount of current. It's a huge value of amount. Start of current starts from 0.5 microampere, not milli, until 1000 microampere. The resistivity will decrease again. Here, it's an interesting one to me. By using the magnetic force microscopy, it's a one-off atomic force microscopy, and it's better it's important here. Here we note the current doesn't change the shape of the ferromagnetic domains, but a few small ferromagnetic domains appear at critical region to bridge large neighboring ferromagnetic domains. Let me explain these few words by use this two images. Here, let's start from here with zero applied current. Some distance between these two or three black points. And after that, when I will start to increase the current, this distance will start to decrease until amount like that of current, all of these distance will disappear to be something like component, something like a bridge. And here, it's another good picture to us. By this union, we have many atoms, many, we can say many cycles belong to metallic, and this, the last one, is isolating. By increasing the current more, this will force this isolating to be metallic atom. That means the magnetic properties will increase by using way like that. Here, at this picture will be the first picture to illustrate to us important thing. This thing is hysteresis phenomena. Here, the idea, I will complain with this component by heating it or warming it from room temperature approximately to approximately 0 Kelvin, and after that dealing with the same component to warming from approximately 0 to room temperature. We will note important things. These things is when calling it to approximately 0 will act like that, and after that I will calling the same the same element to until 300 Kelvin. We will note some difference about the curve between the first one and second one to the same element. This is the hysteresis phenomena. To all of these, and the same thing, the resistivity will decreasing when increasing the current. And here we have two different kinds of electron. The first one is continuous. Just the last one will be plus. That's mean not continuously to maybe to few microseconds. Here we have three critical, I don't know why, we have three critical temperature. The first one is approximately less than 50, let's say 45, 40 Kelvin. And the upper one, approximately 80 Kelvin. And the last one is more than 150. What about this? And the first one, after cross this temperature, I mean here, the hysteresis phenomena will start after warming and cooling. The upper one will be isolating metallic temperature. At this temperature more than 150, the hysteresis start to disappear. This at higher temperature of 150 Kelvin, the change of resistivity becomes almost recovers the original value, like I said before. That's mean approximately the first starting point. Here, it's more good example about the hysteresis. Here, it's very huge, it's very clear. We can take a look about the starting point, and when I'm warming it or I cooling it, it's a huge difference between these two situations. I will start, the Arthur here started from 0.1 milliampere until 30 milliampere. That means the current is increasing like the previous situations, and the resistivity is decreasing. Here's another example with one amount of current, 11 milliampere. we have hysteresis phenomena again. Here, here are this component with the electric resistance. When increasing the current, we note some decreasing in electric resistance. Like I said before, all the articles named at the last of my slides. Here, it's simple example. I'll explain to us the same phenomena. I'm still talking about the hysteresis, about cooling, the blue one, and when warming the same component from approximately 0 until room temperature, we note some different values between all of these. The hysteresis and the thermal hysteresis with these components. Here the summary, like I explained before, the most famous form ABOX or ABO3 about the perovskite oxide, and the electric resistance observed with polycrystalline thin, and the last one is single crystal. The relation about the current temperature and resistance, the resistance temperature curve, like I explained before, and the hysteresis phenomena between warming and cooling. It's important and it's very interesting to me. Then the difference to the contrasting homogeneity of these. Any question? I wish I was good. I wish.
Yeah, yes.
Thanks for your support.
Do you have any question? Okay, Ali. Thank you.
No, thank you too.
Let's go downstairs.
Okay.
And then,
Close my laptop?
yeah. If they don't